Hi, in this video we're going to look at reaction rates from the A-level specification. It's going to look at just a quick recap of collision theory, calculating gradients and how we do that from graphs, how catalysts impact reactions, and then finish off with the Boltzmann distribution. So, key thing with recap of collision theory to begin with is just the idea that a reaction will go faster if there are more collisions. So if we had two equally sized containers with reactants in, moving around, now the chances of these colliding are very small. We need them to collide in order to react. But if we increase the concentration and put more into the same size container, then the chances of these molecules colliding and reacting are a lot greater. So this is the idea of collision theory. The more collisions you can have, the faster the rate the reaction will go at. So in a reaction, you maybe measure how fast the reaction will go, and from that we can work out the rate of the reaction. So this is a practical that's been set up, lots of different ways to measure rates of reaction. This took the mass of the reactants, and as it reacts, this must produce a gas, because the reactant then gets measured and we can check the mass of the reactant, and it's dropping as the reaction progresses. So in this, the rate changes all the way through. Up here, at point A at the beginning, it goes very, very quickly. And at point B, all the way down here, it's almost stopped. The mass isn't dropping anymore at this point, so the reaction isn't going very fast at all. You can get asked to measure the rate of reaction at any point along this graph. So it may say, what is the rate of reaction at 30 seconds? And so to do this, first of all, you've got to go up, straight up for 30 seconds till you get to the line of best fit. Then we have to draw a tangential line. So this is a line that touches the curve at the point we've just marked on, so at 30 seconds, but does not pass through the curve. So that would be tangential. If your line at any point, if you've drawn it and it passes through the curve, then that's not tangential. Same if it passed through at the other side. So you're looking for a line that comes on, just touches, and then goes on. In the mark scheme for the exams, there is a bit of leeway either side for working it out. So we've got our line at 30 seconds. And so this straight line now, the gradient of this stays the same all the way through. And to calculate the gradient, we need to take the change in the y-axis from the 2 points we look at and divide it by the change in the x-axis. So we can choose any 2 points, and it doesn't matter which 2 points you choose. I'm going to just choose 2 at random and then look at whereabouts they are. So this first point's coordinates are, if I call this 1 and this one 2, so 1 is 2.6 grams and 12 seconds. Point 2 is 0.4 grams and 43 seconds. So we need the change in y. So this is 0.4 minus 2.6. What it was at the end minus what it was at the beginning. So we'll have minus 2.2 here. It's lost 2.2 grams between point 1 and point 2. Our change in x is 43 seconds minus 12 seconds, and that gives us, I hope, 31 seconds. So one a negative value, one a positive value. So then the gradient is minus 2.2 divided by 31. If I put that into my calculator, 2.2 divided by 31 equals minus 0.071. Units of this will be grams per second. We've done up here, units here, grams, seconds there, so grams divided by seconds as the unit. And what that means is at this point, along this line, that this is going every second, it's dropping down 0.071 grams. So if you go 10 seconds along on this line, it will have dropped 0.7 grams. At point A, this will be much higher, so you'll get a much more negative value, so it might even be minus 1 gram per second up here, and at B, it'll be very nearly 0 because it's not changing in mass at all. So it'll be the top part of this equation will just be 0, the change in y. So that is how you calculate the gradients from the graphs. Next up, we'll look at catalysts. So again, another thing that was on the GCSE spec, but then goes into a bit more detail on A level. And catalysts increase the rate without being used up. So a catalyst may interact to be part of the reaction, or they're all part of the reaction, and it might even break down into stages into something different, but by the end it'll reform to how it was at the beginning. So if you've got the same amount at the beginning and the same amount at the end, it hasn't been affected. It just might have reacted and become something new in the middle, but it'll go back to its original form by the end of the reaction, if it's a multi-step kind of reaction. They work if we draw quickly an enthalpy profile diagram. Not products, that'll be our reactants and products. And on enthalpy profile diagram, you have your delta H and your activation energy. A catalyst provides a different route than the one we see here. So this route goes all the way up to here, this our activation energy, the amount of energy we have to put in to get a reaction, and then all the way down to here. A catalyst works by providing a different route from the reactants to the products, and this different route has a lower activation energy. I'm going to call it EC, activation energy with a catalyst. So that's lower, so it's a lot easier to do. Less energy needs to go in to get the same amount of product. Next up, we then got heterogeneous catalysts and homogeneous. Big test if I can spell these right. Heterogeneous and homogeneous. So hetero is just different, homo the same. The easy way to remember this. So a heterogeneous catalyst is in a different state to the reactants. So if you've got liquid reactants, a heterogeneous catalyst may be solid. It's most likely in that. So the catalyst is in a different state. Whereas a homogeneous, same state as reactants. So if the reactants are liquid, the homogeneous catalyst will also be a liquid. Then catalysts, really, really important Because if you've got a reaction that you're doing 365 days a year, producing vast amounts, and you have to put energy in order to get this reaction to occur, if you can find a way to do the reaction that reduces the amount of energy required, that's going to save you lots and lots of money. It's also going to help the environment because you're going to produce less waste product. Oh well, more from the heating process, you can have less waste products and less carbon dioxide and things like that potentially going into the atmosphere, depending on how you heat. So there's great benefits in designing catalysts. A lot of money in it as well if you go into that sort of field after your degree. So finally, in rates of reaction, we're going to look at the Boltzmann distribution, which is a beautiful little chart. Up the y-axis, we've got number of particles, and along the x-axis, energy. So at any specific point, if we choose here, at this section of energy, there are lots of particles with that amount of energy. If we go right down here, there are very few particles with very low amounts of energy, and the same over here, the very few particles with this amount of energy. So essentially all the space underneath this line, that represents the number of particles. Not likely that any particle is going to have zero energy. At the temperatures we work at, if there's any temperature, there'll be none at zero. And then also this line never fully gets down to the bottom because there's always the potential for particles to have higher and higher amounts of energy. So it just fuddles on and goes on and on and on forever without meeting the bottom of this line. We also have this line here I'm going to put in, and this is just for any reaction. There'll be a activation energy, and that could be this high up, it could be right down here, it could be anywhere. It helps me to illustrate if I put it where it is now. To the right of this line, so down here, these are the particles with enough energy to react. So these can react. And to the left, in here, these are particles that can't react because they don't have enough energy. They're too low in energy. So that's what the activation energy line tells us. So, two ways we can adapt this. First of all, we can increase the temperature. If we call this T1, if I increase the temperature, the curve changes slightly. Now the area stays the same, but we put in more energy into the particles. So what happens is the area between these two curves is still exactly the same, but now more particles in the second one, just about, have enough energy to react. So all of these, suddenly they can react. That couldn't before. There's less particles now with energy without energy to react. So increasing the temperature flattens down the curve and increases the amount of particles on to the right of the EA line. So that's the first way we can adapt it. I'll just draw on top of it. The second way is adding a catalyst. And if we add a catalyst, as we saw before, that lowers the activation energy. So our activation energy shifts to the left, and suddenly we have, in both of these different reactions, we have all these particles that couldn't react before, but now suddenly can. So suddenly we get a much faster reaction, get much higher yields by adding the catalyst. And that's how you demonstrate either a change in temperature, so an increase in temperature shows that how that will increase the reaction, the Boltzmann distribution, or by adding a catalyst. And that is the rates of reaction.